Hi, everyone. I hope you're all doing okay and having a great day, afternoon, morning, wherever you guys are tuning in from. Today, we have a really exciting workshop, which will be part 2 of Jesse's workshop on using ICP as a Bitcoin layer 2. So I'm just going to invite Alex up from the ICP and he'll be giving his workshop today. Hey.
Hi everyone. So I'm Alex from DFINITY. I'm a software engineer. I work in the team that mainly works on the cryptographic side of the internet computer. And this talk will be about how to use ICP as Bitcoin layer 2. This is part 2 of the presentation. And the previous one was on Tuesday, and you can watch it on YouTube in the same playlist as where you will find this video as well. And you have the QR code that will where you can find these slides. So before we go deeper into the technical details of what I will be talking about, and this presentation will be a little technical, I wanted to first mention again why we want to use ICP in general, like what are the features of ICP and what makes it, why does it stand out? I took the slides from Jesse's presentation, which was the part 1. And yeah, so the main features of ICP, beyond what is kind of obvious, like ICP has very cheap storage where you can really store a lot of information, like gigabytes. And the computation is super cheap. You can compute very complex protocols or algorithms, and I will talk about this a little later, a little more. But some very special features are, for example, threshold signatures that allow you to produce signatures kind of more secure. I'll also talk about this later more. The threshold signatures allow you to use chain key cryptography and chain fusion. And chain fusion is kind of an umbrella term for having assets from multiple blockchains using RPC calls to different blockchains and using this in the context of different decentralized applications, which is really cool. So you don't need bridges, you don't need to trust to different like single parties, and that's why it's cool. You can also produce randomness from or on blockchain. You have decentralized governance, you have timers and heartbeats, and timers means that you can, or heartbeats as well, it means that you can run periodic tasks automatically on blockchain. And you can use HTTPS outcalls, which also means something very specific, very special to this blockchain, as far as I know, that you can really do HTTPS queries basically to the internet from the blockchain directly, which is very cool. The focus of this talk will be 2 things, or actually their intersection mainly. The first one is threshold Schnorr signatures on the internet computer, and the second one is Bitcoin layer 2, and namely Bitcoin Taproot. And their intersection is how to use threshold Schnorr signatures in ICP to hold assets on Bitcoin Taproot addresses in smart contracts on ICP. So this is what I will be talking about. Why is it interesting? Is because Taproot addresses themselves are they require Schnorr signatures in a specific specification, which is called BIP 340, so Bitcoin Improvement Proposal 340. The Bitcoin Taproot addresses have a few benefits. Often they have lower transaction fees. They allow for inscriptions like native Bitcoin tokens, NFTs, and more. And they also have other advantages. But threshold Schnorr signatures do not stop there. We have a few use cases for them. They also allow for to hold assets in different blockchains, not only on Bitcoin. It's possible to hold Solana, Cardano, and other assets where the signature scheme used for transactions is at 25519. And this itself is also really cool because this allows for more chain fusion that I was talking about. And last but not least is that threshold Schnorr is more efficient than threshold ECDSA. If you attended the previous talk, you know that ICP allows for threshold ECDSA signatures, and all Bitcoin address types except Taproot require ECDSA signatures. So by using threshold Schnorr, it's also more efficient to produce, like to make transactions between blockchains, between ICP and Bitcoin. And how we implement this, how we facilitate this, there is a protocol, existing protocol in ICP called interactive distributed key generation. This was initially implemented for threshold ECDSA, and this could be repurposed for threshold BIP340, so this special Bitcoin Schnorr signature type. And by extending it with a new curve 25519, this could also be extended to threshold at 25519. Here is an approximate agenda of what I will be talking about. So I will first go through the basics of Bitcoin threshold signatures and compare threshold ECDSA and threshold Schnorr. I'll explain basically what this talk is about and what this can be used for. And then I'll continue with example dApps on ICP. Three ones. The first one is threshold Schnorr signatures API. So how you use threshold Schnorr API on ICP to sign anything, and to like how do you retrieve public key. So very simple example. The second one will be about how you perform Bitcoin Taproot transactions on ICP using threshold cryptography. And the last one will be about Bitcoin inscriptions from ICP. Yeah, so first, the background. The very basics, let's start with them. So there are a few different Bitcoin transaction types and address types. They can be categorized into two different categories. The ones that require ECDSA signatures and the ones that require Schnorr signatures. The first one, so the ECDSA signature-based addresses, I will just mention three. There are more, but this, as far as you know, these are the most popular ones. But I'm not an expert in Bitcoin. So the first one is called P2PK, pay to public key, where you have public key in the address. The address is quite large, so you pay a little more fees for transactions. And the big limitation here is that you cannot use any scripts, so no complex spending rules. The second one, and I think this is actually the most popular one, is pay to public key hash, also sometimes with witness, which is just like wireless fees. Probably also can also use witnesses with the previous address, but I'm not really sure, and it's probably also not. That doesn't really matter that much for this talk. So in this pay to public key hash, you have this is already an improvement over the previous address. So you have just public key hash in the address, which is smaller, but still there are no scripts. And the last type of ECDSA addresses I wanted to mention is pay to witness script hash. And here you can have scripts. And the address is also quite small, but it's as far as I know, it's not very cheap to spend from these addresses. And you also need to reveal all script conditions. If you want to spend, so if you have multiple ones, you will need to reveal everything. And also the scripts that can be implemented with this are very limited. So for example, you cannot use inscriptions with P2SH. because they basically whitelist the type of scripts that you want to use. And this brings us to the other types most relevant for this talk, which is P2TR, P2 Taproot, and this requires Schnorr signatures. There are two kind of native ways of spending from this address. The first one is spent with the key, the simpler one kind of, and it's also cheaper. I'll give you some illustration of how it looks like in, I think, next slide. There is also a possibility to spend with a script. The scripts that are available for one address are stored in a Merkle tree, a data structure, where you have in the leaves independent spanning scripts. And Merkle tree data structure allows you to reveal only the script that is needed for spending, and there's still you need a little more information than just the leaf, but you don't reveal anything in the clear text, this allows you basically to just reveal whatever you use. And if you don't want to reveal the other scripts, you can just never reveal them to the Bitcoin nodes, and no one except you will know about them, about their content. Taproot allows you to store arbitrary data in scripts, which allows for inscriptions like NFTs and other cool stuff. And here's how Taproot addresses look like from the inside, kind of. So there's this Taproot thing, which is just a hash. And this is a hash over a particular data structure that contains the internal key and the Merkle tree root. So the root over all scripts, basically. And you compute the address for this content as the internal key plus the Taproot hash. And the plus operation is actually it just produces another public key, and the public key will be the encoding of the address. So the address is the encoding of a public key, which is used for spending with keys. And on ICP, you have currently actually two options how you can spend from this address. The first one is called raw key spend, and here this is kind of it's not an edge case, but it's kind of a rare case of how to use Taproot. But this is actually the most efficient one. And here you say, instead of having Taproot, you just say I don't have any Merkle tree, so I don't need a Taproot. I just have the internal key, and you say address is my internal key, and you ignore the Taproot in general. This allows, so there are limitations. So this allows only for single signer, and this doesn't allow for scripts. Then there is the second option, which is using scripts. And here, this is a specific use case for scripts. It's not a general way of spending. The limitation here is that you cannot use the key path. And why is it bad? Is because using scripts is in general less efficient. So it costs more in terms of fees, in terms of Bitcoin fees. And there is the third way, that is the generic one. So you can use whatever you want there, internal key, scripts. This is currently not available on ICP, but this is work in progress. There is no technical limitation. This was rather a matter of prioritization, so it comes soon as well. Yeah, so let's talk briefly about what signatures and threshold signatures are, and in particular on ICP. So everyone knows what a signature is, how to produce one. User holds the private key and signs locally something. And this is secure as long as no one knows the key, except user or some trusted devices. And this is different for threshold signatures. So there is no single user that holds the private key in clear text. But here there are multiple nodes who hold shares of the private key, and no one ever will see and know the clear text key. how they sign then, they do this in an interactive protocol, an interactive cryptographic protocol. They actually also don't produce a signature, but they produce shares of the signature. And they reconstruct them by basically broadcasting the shares, and they can then reconstruct it. And this is secure as long as less than 1/3 of the nodes act maliciously. So now, again, what's the difference between, or what's in common for threshold ECSA and threshold Schnorr on ICP? Both protocols generate something called pre-signatures, and those pre-signatures are independent of the key and message. So you can really generate pre-signature and use it immediately as some client, some canister, which canister is a smart contract on ICP, basically ask for a signature for some key and some message, and you can use that pre-signature. Both protocols also use IDKG, which is this interactive distributed key generation protocol, to generate those pre-signatures. The difference in threshold Schnorr is that it needs only one IDKG operation, while TCSA needs 4, because the pre-signature basically contains 4 different parts. And because of that, because there are 4 parts, and the equation for computing the signature, so you have the pre-signature, and there is some function that you use to compute the signature. And this function implements some mathematical equation, and this equation is just more complicated for threshold ECDSA. So not only you need fewer IDKG runs, but you also can construct the signature with less compute, so basically with less latency. Why is it interesting to have? Why is it useful to have Taproot on ICP? So the same reasons apply as for threshold ECDSA and Bitcoin. It's very cheap layer 2 Bitcoin operations. You can have distributed wallets. You don't need to trust any third parties. And smart contracts define how to spend Bitcoin, which is really cool. Threshold Schnorr is also cheaper than ECDSA, so this is another argument for implementing Bitcoin transactions in layer 2 with threshold Schnorr. And smart contracts define how to use inscriptions here, because only Taproot can create inscriptions. Why is it cool? So you can, this just like you can, only your imagination limits you here, probably. At least for me, this looks like this, because you can really go crazy here. You can have, I don't know, like in the smart contract, so in the canister on ICP, you can have some AI that asks Google automatically each day for like what happened today. It can generate some image and create NFT out of that completely automatically without any user interaction. So you can really do crazy stuff that usually is not absolutely not available for blockchains. Yeah, let's move on to the system API of threshold Schnorr. It's quite simple, and if you've ever looked at the system API for threshold ECDSA, it is actually very, very similar. There are only 2 functions, assigned with Schnorr and Schnorr public key. Maybe I should say a few words about how the key derivation works. So on ICP, you have multiple subnets, and each subnet runs separate consensus. And here we, using this decentralized government, we create a shared key. For example, Schnorr BIP340 distributed key at some subnet and call it somehow. We always have a key name. You see here, we have key ID, and inside we have an algorithm and a name. And the algorithm would be BIP340, and the name is, for production key, currently is key 1. And this gives the subnet its root key. So this is actually a root key name. What happens next is each canister for each canister, the subnet derives its own subkey, and each canister from that canister key, it can derive as many subkeys as necessary. But when the canister calls sign with schnorr, it can only sign for itself. So basically, it cannot sign for some other canister. It's basically impossible by design. And what happens here in this sign with schnorr? Some canister just says, I want to have this message signed with this key ID, root key ID, and some derivation path, and it gets back the signature. Then the same canister A or some other canister B can call schnorr public key for canister A. For example, canister B says, I want to have the schnorr public key for canister A for key 1, BIP340, and derivation path something, I don't know, just username, something like this. And it gets the public key. So public key can be obtained for any canister because public API. And management canisters here is not real canister. It's basically some kind of system canister that basically is, I would say, rather a router for different functionalities that the system interface provides, which just routes the calls to the right places. Then we also have a few keys currently deployed on ICP. There are 3 production keys and 3 test keys. The difference between the production keys and test keys is actually not that big. So at least in terms of costs, the test keys are more for like production testing, like real world testing. There will soon be something called chain key mock canister that costs almost nothing to call, but it's also insecure. So test key is secure, but the security assumption is just different because the security of the threshold keys depends on the number of nodes in the subnet, and the production keys are deployed in the larger subnets, and test keys are deployed in the smaller subnets. I think currently production subnets are like 34 nodes. And we have production test keys for ECDSA, and 2 pairs for schnorr, BIP340, and ET25519. Let's then continue with the example dApps. Oh, I'm actually much faster than I expected, but yeah, so there will be 3 example dApps I'll be talking about. The first one is the threshold schnorr example, which is about just the plain API of the threshold schnorr. I will show how what kind of API we have there for signing with schnorr and for retrieving the public key, but I also show like the signature verification. The signature verification is not part of the system API because this can be done locally. There are 2 different examples, one for Motoko and one for Rust. Motoko, if someone doesn't know, is a language, it's a smart contract language specifically designed for ICP. Why do we need this? Like everyone knows what Rust is. Not everyone knows how to use Rust. So if you want if you've heard that Rust is kind of a cool new language and you want to use it for smart contracts on ICP, this is like no problem. But this requires you to learn Rust first, which is not very fast usually. And you also afterwards need to learn how to use Rust for programming smart contracts, which is just 2 steps. And Motoko removes that intermediate step. And Motoko was designed for smart contracts on ICP. And this simplifies this a lot. So usually this is faster to learn Motoko. Then the second example will be about this basic Bitcoin, where this is basically about the Taproot addresses mainly. It is also code in Motoko and Rust, and there will be a very short overview of the Bitcoin inscriptions example, where we can create Bitcoin ordinal inscriptions from a canister. So I just made a screenshot because it's faster than clicking on the same things. It's also a very simple interface. So in the threshold schnorr example, we can retrieve the public key. We just use empty derivation path. So it is using the root canister key. Here we can choose from BIP340 and 25509. We just click on call, and this gives us back the public key hex representation. We can call sign for also, again, for both algorithms. Everything can be done here for both algorithms. We can call sign, and this gives us the signature hex representation. And then we can verify this. So this is always using the root keys, and you can always use any or one of the available algorithms, Schnorr algorithms. And for verification, just copy paste here the signature first, then the message and the public key, and this gives you back if the signature was valid. Yeah, you can just scan the QR code if you're interested, and there is a description of the code, of how to use it, and also link to this canister. So yeah, feel free to check it out and try it out. Yeah, so it was very simple. I'm sorry if it was too simple, but the next one will be a little less simple. So here I have here two pieces of information for you. On the left-hand side, there is some code for signing the Taproot transaction. And the right-hand side, this is the architecture of this example. Let's first start with the code. Like what I wanted to convey here with this code is how simple the change is if you transition from not using ICP and using the ICP. So here we have the transaction. There are some information that are not relevant for the signature, for the signing itself, so just omitted it. There is the transaction information. It is pre-computed. The only thing missing here in this transaction variable is the signature itself. So all the information is already there except signatures. We have there also the key name, the version path, as I told you before, the information that we need. And on Bitcoin, in order to sign a transaction, you produce one signature for each of the inputs. That's why I'm interested in the number of inputs. We go in a loop for each of the indices of the inputs. We produce the signing data. We use for that the Bitcoin crate. And Bitcoin crate, like if you don't know what Rust is, so crate is just a library. So basically we use a Bitcoin library to create signing data. We just put the information that we want to sign into there, and it just gives us signing data. We call this Schnorr management canister API with the key name, derivation path, and signing data. And this gives us back the signature. And we put the signature in the same way as we would put the locally signed signature into the witness. Witness is just the place where you put signatures nowadays. And the only difference to the plaintext API would be that you don't need the key name and derivation path. We just need the signing data. Instead of key name derivation path, we just pass some key reference, for example. Yeah, so this is really this simple. For Motoko, there's also a library for constructing signing data, so it also works there. Quite simple. How this works on the architectural level. So there on ICP, there's a specific term, asset canister, which is just a specific storage for different assets, so basically for data. And what a user does here, the user fetches the front-end data for its browser from the asset canister, and the user can then use the front-end, and the front-end knows how to communicate with the basic Bitcoin example canister. So this is this example. And it can do just normal Bitcoin stuff, like get address, send from address. Yeah, so just normal APIs. I'll show you just in a few minutes what kind of APIs we have there. And this canister can, it uses Bitcoin API and Schnorr API of the management canister. And behind management canister, there is some complexity behind it. It's not very interesting for the presentation, but just for completeness, there is some Bitcoin adapter that communicates with Bitcoin testnet. Unfortunately, I cannot show you the demo because testnet goes crazy currently, but please trust me, it worked. I'll show you transactions from one of the previous demos. Yeah, so this is the canister. It's also, you can also go to the code, to GitHub, and you will see there the description again and link to this canister, I guess, if I recall correctly. And here we have just a few pieces of API. We can get balance of any account. Currently we cannot because, yeah, again, testnet. We are currently trying to fix this and migrate to another testnet, but currently it's not usable. You can get current fee percentiles to try to estimate the a fee for your transaction that is not too high, not too low. Then you have three different getter methods. The first one is for pay to public key hash address, and the second two ones are for Taproot addresses, the same types of addresses I described before. So this row or untweaked key span that cannot use scripts, and the script spans that cannot use keys, basically row keys. You can get the unique source of any addresses on that network, and you can send from any of those addresses as well, send tokens. So let me just query the addresses. So this is the pay to public key hash address, and I was sending here from, I'll show you, from the row key address, I was sending to this address. So this is mixed spending, kind of, because this is another type of address. I was sending 10K Satoshis. And the rest was, wait a second, this one. The remaining ones were sent as change of that UTXO to the same address. So it's on testnet. It was confirmed, so everything worked fine. And yeah, so this is basically it. So this is how it works. Did I forget anything? I don't think so. Yeah, so that's how it works. Check it out if you're interested. And the last thing I want to talk about is Bitcoin inscriptions. So there is a Rust implementation for this. It's only in Rust because there were already existing tools in Rust for ordinals. Here's the user interface. It is only using currently a reg test, so only local tests. It's just for simplicity, so if you're interested, just feel free to extend it. There's some address of the Bitcoin address for this canister. There is some balance of the canister. You can top it up because it is everything is local. Check balance. There is the current block height displayed. Why is it important? Is because you can generate, can create new valid inscriptions only after some blocks are produced. And you have some recipient address. You just this can be any type of address. The only important thing for Taproot addresses is that these are the only addresses that can create inscriptions. You just select here the content type, for example, text, hello world. You press inscribe, and this produces a new inscription. How this works, just for completeness. So there is a script like this. So it's always the same structure. You have a op false statement that is just put on stack. Then you have the if statement that reads this false, and this if statement basically never gets evaluated. But inside you have the data for the inscription. You have ord, which is ordinals. I don't remember what the digits here are, but you basically say here, I want to input some text, and the text is hello world. And that's it. This is the inscription. Usually here at the end you have also the signature check, so that you know that, so the Bitcoin node knows that you can spend with using the script, using your private key. And so this actually needs two transactions. The first one is called commit transaction, where you create the address. So you say, I have some internal key, I have the script that contains my inscription, but what Bitcoin node sees is just the address. So it transfers some funds to this address, and the address becomes valid, known for the Bitcoin network. But no one knows the script currently because it's privacy preserving. What you do next is you make a transfer from that created address to somewhere else with this script that is here above. And this makes the inscription valid. And you can do this on the ICP, from the ICP directly to Bitcoin without any bridges. Yeah, if you're interested, check it out. And I think this concludes my presentation. Thank you, and I'm happy to take questions.
Amazing. Thank you so much, Alex. I think there are 2 questions in the chat. Evan's asking where the GitHub code is, I think.
So again, if I heard this correctly, where the code is for the examples.
Yeah, the GitHub, yeah.
Okay. So basically, if you go to, if you scan the QR codes, this will be the same repository. This will be a GitHub DFINITY examples, if I recall correctly. Actually, these ones. So very simple, DFINITY examples. And this will just lead you to different parts of the same repository. There is a big directory Rust, there's a big directory Motoko with many examples. And sometimes, I'm not sure if I did this here, but sometimes even to different parts of the code of the same example. Yeah.
Amazing. Thank you. And Mohammed was asking, Bitcoin inscriptions, is it not possible with Motoko?
Bitcoin inscriptions are possible with Motoko. I'm just the complication here is just that you will need to describe in Motoko. Very likely, you will need to describe it yourself how to create an inscription. So you can. We have a library for creating transactions, but creating inscriptions is kind of higher level algorithm for transactions. So it's basically a specific algorithm for creating specific scripts for Taproot. So this someone needs to implement.
Amazing. Mohammed was saying, are the necessary libraries present? That's what he was getting at.
For Taproot, yes. So you can do the transactions, but there are no libraries for creating particular scripts for ordinals.
Great. Amazing. Another question. Evan says, curious to know what can Bitcoin do where and at what point can we try to integrate it with ICP?
So if I understand the question correctly, you can basically hold Bitcoin assets, so Bitcoin tokens on ICP. How this is done, you basically have a Bitcoin address in a canister on multiple addresses. This is possible because of the threshold signatures. So here, no one knows the private key, but the canister can sign something on behalf of that key. Why this is secure? Like if you want to create your own dApp, you will need to open source your code so that other users, at least part of your code that are security related, so that the users can check if the code does what it's supposed to do. So, okay, the another question is like, Mohammed asks if you have any examples of what may be good sample projects for us to pursue for the hackathon. Got a few ideas, but it would be good to know what the current feel and need is within the ICP community. I think this is more a question about the Bitcoin community and what people outside of the ICP community like, because there are, for example, the obvious things are decentralized exchanges, so you can exchange tokens, obviously, but otherwise, like NFT marketplaces, I think would be interesting. Just like this should be something that brings some value to Bitcoin. And the main downside of Bitcoin is usually that it's slow. It's slow and expensive. So if you find something that is faster and cheaper, then this is really something cool to do.
Amazing. Yeah, that's great help. Evans also asked another question.
Yeah, so we are using Bitcoin for security reasons. What else can we need to be? Because it is my first time I want to build using Bitcoin. I'm not sure if I understand the question correctly. So we're using Bitcoin for security reasons. To be honest, maybe Evans can rephrase this.
Yeah.
So yeah, obviously Bitcoin Bitcoin security model is very robust, but this very robust security model also makes it very, very slow. So there are many ways of using Bitcoin and ICP. For the simplest way, you can check out the basic Bitcoin example code. This quite nicely showcases how to move assets from Bitcoin to ICP. Otherwise, there's the inscription canister code that allows you to build inscriptions, but you need to provide the rules for inscriptions. You need to say, I want to have text here, I want to have an NFT, I want to have BERC20 tokens. This is a good question. Like you have a lot of freedom here. So again, if you want to use Bitcoin, this is usually about improving the limitations of Bitcoin. So this is usually about fees and latency of transactions. This is what ICP compensates for usually.
Evans is still typing. Let's see if he's got another question.
Sure. But also, like after this presentation, you can also go to the DFINITY forum. The community is usually quite active, so you can just type your questions. Usually, there is some discussion. If there was no discussion yet, there likely will be. So, okay, so if I can repeat the aspect of Schnorr, you mean the advantages of Schnorr? Of threshold Schnorr? Okay.
Just to remind, this workshop will be recorded and uploaded tomorrow, yes. So you will be able to watch this as many times as you want as well. But yeah, carry on.
So the advantages of Schnorr are that, like, okay, so threshold Schnorr is one thing. You can use threshold Schnorr for signing Bitcoin transactions for Taproot. This is one aspect. And the second aspect of threshold Schnorr signatures is that there are many kinds of Schnorr signatures. For example, 82519 allows you to do the same as with Bitcoin, but with Solana and other assets. Why it is interesting to have Taproot, to use Taproot in particular, it is because, like, compared to, for example, the same ECSA signatures, like different types of addresses. I guess maybe let me open the slides again briefly. This one. So yes, so for Bitcoin in particular, we have much more efficient signature protocol. It's very roughly 4 times more efficient, maybe a little more than compared to ECSA. This usually means that if there is much load, if there is much usage of threshold Schnorr signatures, there will likely be cheaper. Then why exactly Taproot on ICP? So why not just use specialty CSA? This is faster than CSA, as I mentioned before, and also this allows for inscriptions from smart contracts. So you can kind of automate the inscription creation or let the smart contract decide how to manage, for example, BRC20 tokens. So this allows for automation and not just like user control. This is basically the main point.
Great. Thank you so much. If there's any more questions, now is your time to ask. But like Alex said, in the DFINITY forum, they'll be able to help you with that. We also have some members from the ICP team in our Discord, so they'll be able to help you with any technical questions. And yeah, like I mentioned, all workshops are recorded, will be uploaded. And yeah, that's it for us this week. Next week, we've got our final workshop with local mining. And yeah, I hope you all have a great day. Alex, thank you so much for your workshop. It was great and super informative. And I hope to see you all next week. Have a great day, everyone. Bye-bye.
Bye-bye.